Section 6, GPU computing systems with NVL72. In this section, we are going to discuss the two possible programming models for NVL72. Okay, we start with NVL1. What's the meaning of NVL1? And later on, because we are going to discuss NVL72, so what's the meaning of NVL72? Okay, well, the definition is that if you have multiple GPUs in a system, and if you use NVLink interconnection to interconnect all these GPUs together, then the GPUs and the NVLink network that has been used to interconnect all these GPUs all together, the GPUs and the NVLink network are called an NVLink domain. So it's called an NVLink domain. Okay. If you have 72 GPUs and you are going to use NVLink network to interconnect all these 72 GPUs together, the 72 GPUs plus the NVLink network for the 72 GPUs all together, they are going to be called an NVLink network with 72 GPUs for short, and this one is going to be called NVLink 72. So that's the definition of NVLink 72. The same thing is for NVLink 1. NVLink 1 is very simple. You have an NVLink domain, but in this domain, you have only one GPU. Okay, so Grasshopper reference architecture for NVL1. One Grasshopper superchip could be used as a node. If you use only one Grasshopper superchip as a node, and this node, there is a code from Nvidia for this node. It's called CG1. Okay. And this is the physical, this is the photo of a CG1 node. Here is an Nvidia HGX Grasshopper CG1 node with InfiniBand. Okay. This is the photo of the node. Here, what you have is a logical architecture of this CG1 node. This is the CG1 node. Basically, what you have is one CPU and one GPU. The CPU and the GPU are interconnected by this C2C network. This is a CG1 node. And then the text has mentioned that this node on this photo, this node has an InfiniBand as the network. But here, on this logical view of the node, it has been marked as BlueField 3. But that's not the trouble, because as a user or as a system vendor, you have the choice to propose either BlueField 3, or you can propose InfiniBand to the customer, or the customer can choose to use InfiniBand. So we are going to suppose that we are going to have a system with InfiniBand rather than BlueField and as the interface, and you are going to have a system like this to be consistent with the text here, InfiniBand. And you are going to have the interconnection network. Pretty much the most popular one is the InfiniBand. And then the system is done, and then the communication. We need to come back to this NVLink 1. Okay, NVLink 1 means that you only have one GPU for NVLink domain. That means what? That means NVLink 1 means 0 NVLinks. No one NVLink between GPU, because you have only one GPU. There is no others to be connected to the GPU by using NVLink. So you have only one. Actually, NVLink 1 means no NVLink, no NVLink between GPUs. Okay, so this is a reference architecture of the system. Here, you can note that here you have the number of nodes for this system is n. So you can choose an arbitrary number of nodes for your needs if you have the system with, for example, with 1,000 nodes, 1,024 nodes, and that's possible. You can just do that, and you are going to build up an interconnection network for all these nodes, and the system is going to work for you. Here we have some advertisement from Nvidia. It basically is saying that this CG1 node, this grasshopper with InfiniBand, is ideal for the scale out of traditional machine learning and HPC workloads that are not bottlenecked by network communication or heads of InfiniBand. Okay, so if you have InfiniBand, basically Nvidia is saying this network is good for these two kinds of workloads. Okay, so that's fine. But there is a case that maybe there is the need for this GPU to communicate with another GPU. For example, if GPU 0 wants to communicate with GPU 1, or GPU 2 wants to communicate with GPU 3, or GPU 2 also wants to communicate with GPU 4, that's possible. The same thing could happen that CPU 1 wants to communicate with CPU 2, etc., etc. All this has to be done by the InfiniBand. All this has to be carried out by the MPI library. So the program has to use MPI type library to take care all these needs of communication. If we just stop a minute to think about at the very beginning, more than a decade ago, when Nvidia started this GPU computing, there is a difference between the CPU memory, let's call it the CPU memory, and it's also good to call it this host memory, and the GPU memory. For Grasshopper, the host memory is DDR, LPDDR, and for the GPU, the memory is HBM. As very beginning, you know that we have a trouble because if you remember in section 3 and section 4, we have discussed the two different kinds of MPI library. One is GPU aware MPI library. The other one is non-GPU aware MPI library. GPU aware MPI library. This MPI communication scheme, it can take the data from the GPU and send data. Take the data from this GPU and send data to GPU 1. All these are going to go through this InfiniBand network. It's going to be done this way, from GPU 0 from the HBM memory to the HBM memory in GPU 1. This is for GPU aware MPI library. For non-GPU aware MPI library, it can only take the memory from the host and do the communication and put data in the memory of another host. It cannot put the data into the memory of the GPU. So there are two kinds MPI library at the early days of the GPU computing. But with the architectural evolution right now, this difference between the MPI library and the difference between the non-GPU aware MPI library and the GPU aware MPI library doesn't exist anymore for Grasshopper, because for Grasshopper, actually the the host memory and the HBM, and what I mean is that the host memory and the GPU memory has been virtually unified. So you have some kind of virtually unified memory. So right now, there is no difference for the MPI library, whatever the MPI library, because the memory has been unified. There is no difference between the host and the GPU regarding the memory. So MPI communication scheme is going to be simplified. Every MPI communication scheme, every MPI library could work with this kind of Grace-Hopper system, because there is no more the difference from the MPI communication schemes point of view. There is no more difference between the host memory and the GPU memory. So right now we don't have this kind of differentiation between non-GPU aware MPI library and the GPU aware MPI library. Pretty much the MPI library that works on these Grace-Hopper systems is going to work with both the host and the memory, the host and the GPU memory, and there is no more trouble for this MPI communication scheme to take care of the communication between the hosts. What I mean by between the hosts means between the CPUs and the communication between the GPUs. There is no more trouble for MPI communication library to take care of this kind of communication needs. So this system, this referenced architecture, this system, it works well with these two kinds of workloads. So this is the NVL1. Now we move to another extreme, which is NVL 256. Again, this is the Grace-Hopper reference architecture NVL 256. You have one Grace-Hopper superchip, as this is called CG1. You have one CG1 as a node. And this is the logical architecture. This is the same as the previous section slide. Here, NVL1, and you have a logical, you have a node. It's like this, and we have the same node as NVL1. Okay, the difference is that right now you are going to have an NVL domain with 256 GPUs. So 256 GPUs means 256 Grace-Hopper superchips. So here, what you have is Grace CPU and Hopper GPU. That makes a Grace-Hopper superchip. 256 means that you have the last one. The ID of the last one is 255 and 255. Basically, altogether, you are going to have 256 GPUs. Okay, you have only GPUs that doesn't make NVL 256 domain. What you need to have an interconnection network which interconnects all these 256 GPUs, and these 256 GPUs plus this interconnection network, all this together is going to give you this NVL 256, this NVL 256 domain. Okay, so there's another extreme. And for the communications, okay, there are two parts. First one, the communication between the GPUs. If you still remember, in section 4 and section 5, we have discussed the two possible communication schemes for for GPUs, intro and NVL domain. Okay, intro and NVL domain, you have two communication schemes. One is the NICO, by using the NICO communication library. Another one is the peer-to-peer memory access. Attention, what we are saying is that in Section 4 and Section 5, we have discussed two possible communication schemes for invalid domains. But for those two sections, up to now, the invalid domains have never has never been caused nodes. In Section 4 and Section 5, we have been always discussing invalid domains that belongs to only one node. So before the Grasshopper system, NVL domains can only be attached to one host. For example, if you have 8 GPUs, for example, we take the NVL, we take the Nvidia SXM module as an example. If you got an SXM module from Nvidia with 8 GPUs, and this module, you are going to connect this module to an x86 node. You are going to make one node. There is only one node. And the 8 GPUs connected to the host, and then at the same time comes together with Nvidia for these 8 GPUs on the same SXM module. There is going to be an NVLink network, pretty much that's with 3 NVLink switches plus the interconnect, the links, and this NVLink network is going to interconnect all these 8 GPU together. That's going to give you an NVLink domain. And the NVLink domain, this NVLink domain is NVL8. And that belongs to the single node. So maybe it's better to draw a picture here. If you have x86, you have a server with x86, and you are going to connect to this memory, and you connect to the memory, and the GPUs, the CPUs are going to be interconnected each other. This is a node. Okay, this is a node, and what you are going to, and you are going to get an SXM module with, let's see, you have up to 8 GPUs with GPUs. You have all these GPUs, and these GPUs are going to be connected to the CPU by using PCIe links. Okay, but then it's a node. Here, what you have is a node. It's a node, and then comes from NVIDIA together with the SXM module. You are going to have NVLink switches, NVLink switches, NVLink switches, and the NVLink switches is going to be connected to all these GPUs. Okay, so this NVLink switch here, the links and the GPUs all together. This is an NVLink domain. Here you have 8 GPUs. This is an NVLink 8, NVL8 domain, NVLink 8. But before superchip, before the Grasshopper superchip, this NVL domain whatever the number NVL4 or NVL8, this NVL domain belongs to a node. So here is the node. This NVLink domain belongs to the node. The NVLink domain here has never been across nodes. That means this NVLink A domain has never been connected to two nodes, has never been connected to more than one nodes. For example, to two nodes or to three nodes or to four nodes. It has never been done. NVLink domain can only belongs to only one node. That's the case up to Grace Hopper. For Grace Hopper, the things has been changed. Here, you can see very clearly that this NVL 256 domain, this NVL 256 is crossing nodes. So this NVL 256 domain is connected to 256 nodes. So they have the first node, the second node, you have the last one, which is the 250, sorry. You have the 256 nodes. This NVL 256 has been connected to 256 nodes. So since Grace Hopper things has been changed, the NVL domains could be connected to more than one nodes. Means the NVL domains right now could be crossing nodes. Okay, this is a very important evolution that's since the Grace Hopper superchip. Afterwards, with Grace Blackwell, it's the same story. Afterward, it's the same story. I think after Grace Blackwell, with other next generation of products, the things will be the same. So we need to bear in mind there is this technical evolution regarding these NVL domains, because this is important for this section, and this is important for our discussion. We just need to bear in mind all this. Okay. And but there is but since the very early days, even with this kind of system, there are two kinds of communications that's possible within an NVL domain. First one is that the communications between the GPUs. What you can do is that you can do this. You can use this NVLink network to send message. If GPU 0 wants to communicate with GPU 2, one way to make the communication is that by using this NVLink network. If your GPU 1 has to communicate with GPU 7, one way to do it is by using this NVLink network and by using the NICO communication library. So here you have this NICO. You have this NICO. This is the NICO communication library. One way to do it, to do the communication for all these GPUs, is by using NICO. Okay. The second way to do this kind of to do the communication between the GPUs is using peer-to-peer memory access. So the GPU 0 wants to communicate with GPU 2. One way to do it is by using NICO. Another way to do it is to do the peer-to-peer memory access. GPU is going to directly read the memory of GPU 2. This is peer-to-peer memory access. It is going to read directly the memory of GPU 2. GPU 1 is going to read directly the memory of GPU 7. This is the peer-to-peer memory access. Okay. There are two ways to do the communication for all the GPUs belonging to only one NVLink domain. This is the case. It's still the case for all the non-Grace Hopper GPU solutions comes from Nvidia. And now, if we move to Grace Hopper, is still the case. So there are two possibilities to make the communication happen between any pair of GPUs from this NVLink domain. So this NVLink domain, if you want the GPU 0 wants to communicate with GPU 1, one way to realize the communication is by using the NICO. And the NICO communication is going to use this interconnection network, the NVLink in interconnection network. Here it is. This is the NVLink, NVIDIA NVLink switch system, and that's the NVLink network. So one way to do the communication is the NICO, and then the same as the early days NVLink domain that belongs to one node. There is the second way to make the communication happen is the peer-to-peer memory access. These two schemes of communication, they didn't change. They remains. They are going to be available for Grace Hopper solutions, but there is a difference. The difference, all this difference comes from the fact that since Grace Hopper, the NVLink domains could be crossing nodes, and this is case for the reference architecture NVL 256. Okay, this NICO and the peer-to-peer memory access is going to be our discussion for the following parts of this section. Okay, that's for the communication intra-NVLink domains. But the fact is that if you have multiple NVLink domains per system, okay, you have the first NVLink 256, you have another NVLink 256 domain, you have another NVL 256 intra-list 256 NVL 256. You can do NICO, you can do peer-to-peer communication for the GPUs. But at the same time, there is a need for the CPUs to communicate. Okay, the same as previous slide for NVL1. For the CPU communication, what we need to rely on is the MPI communication scheme. So from CPU 0 to CPU 1, or from CPU 0, for example, to the last one, CPU 255. You need to have the communication, and this communication between the CPUs. Another one, this is the communication between the hosts. This communication has to be done by using the MPI communication scheme. So that means you have to use the MPI communication library. Suppose for the industry is pretty much familiar with the InfiniBand. So I suppose we are using InfiniBand here. InfiniBand here, InfiniBand here, InfiniBand here, and between all these nodes, between all these hosts, intra and NVL domain or inter-NVL domains, the communication between the hosts will always be by using this MPI communication scheme. Suppose you have here is InfiniBand network, and you are going to run this MPI communication library on top of this InfiniBand network, and the communication between the nodes whatever the nodes, intro one NVL domain or inter NVL domains, the communication will be done by using the MPI library. So for pretty much for grasshopper systems, for these huge systems, if you have an NVL domain that's not NVL1, you need to have the NICO and the peer-to-peer memory access. But at the same time, you also need to have this MPI communication library. Okay. So Nvidia here is that there is some peeps. There are some advertisements from Nvidia. This is the text I have taken from the Nvidia website. Basically, Nvidia is saying that this HGX grasshopper with NVLink switch is ideal for strong scaling giant machine learning and HPC workloads. Okay. And it described that NVLink connected domains, so NVL 256. So NVL 256 for our particular example, these 256 GPUs are networked with Nvidia networked with, oh, sorry, I made a mistake. It basically is saying that the NVLink domains, so on this picture, on this drawing, we have two NVLink domains, the left-hand side one and the right-hand side one. So NVLink connect domains, we have two NVL 256. NVLink domains are networked with NVIDIA InfiniBand networking. For example, it mentioned three technologies. It mentioned two technologies, and we used Connect X as an example because this is the InfiniBand. Connect X is the InfiniBand. So we use the InfiniBand as the example. So NVIDIA domains are networked with NVIDIA InfiniBand networking. That is talking about this communication between NVIDIA domains. But we need to have a look of this NVIDIA domain. For this NVIDIA 256 domain, okay, this NVIDIA 256 enables all GPU threads in the NVLink connected domain. In the NVLink connected in the NVL connected domain, for our example, for this NVL 256, this NVL 256 enables a thread, every thread, all GPU threads, because you are going to have lots of threads. The GPU threads is going to enable, we take this one as an example. This is the GPU thread. It is going to enable the GPU threads to address up to 150 terabytes of memory at up to 900 gigabytes per second. We need to take these two numbers, 150 terabytes memory and 900 gigabytes per second. Basically, it's saying that the threads running on top of this GPU, the threads running on this GPU can access the memory of its own, memory, HBM. It can also access the host memory. At the same time, it can also access all the host memory. Sorry, it's not so clear. Okay. Host memory, and GPU memory, HBM, GPU memory. Basically, it's saying that The thread can access its own HBM, its own host memory, and thus at the same time, it can also access all the host memory and the GPU memory of all the nodes belonging to this NVL domain. And the sum of all this memory for this NVL 256 is, so we continue. Basically, it's saying that the threads on this GPU can access, the threads on each of the GPU can access its own GPU memory, its own host memory, and plus all the host memory and all the GPU memory belonging to other nodes. And if you do a summary, all this memory, the total quantity is going to be 150 terabytes for 256 Grace Hopper GPUs. And the bandwidth for the memory access is going to be limited by this NVLink, which is 900 gigabytes per second for Grace Hopper. So basically, we take these two numbers, 900 gigabytes per second and 150 terabytes of memory. This is for peer-to-peer memory access. We put the number here, terabytes and gigabytes per second. This is for peer-to-peer memory access. Okay. Okay. If you use peer-to-peer memory access as your programming model, then you are going to have a simple programming model uses pointer load, store, and atomic operations. Okay. And then we come to this NICO part. For this NVLink communication library, for this NVLink communication network. Okay, here, this is NVLink communication network, it has been shown here. For this communication network, it has 450 gigabytes per second as the all reduced bandwidth and 115.2 terabytes bisectional bandwidth. Okay, so for this NVL 256 domain, the NVLink network has 450 gigabytes per second as the all reduced bandwidth, because basically this 450 gigabytes per second is half of this NVLink link. So it's always half. So the all reduced bandwidth is always the half of the 900. And depending on the size of the NVLink network and also depending on the technology used, the bisectional bandwidth of this NVLink network. For this NVLink 256 domain, the bisectional bandwidth is going to be 115.2 terabytes per second. Okay. In this text, we have got these two parameters. One is for the peer-to-peer memory access. The other one is for this NICO communication. You have these two parameters. Okay. Now, this is for the NVL 256. We are going to discuss the peer-to-peer memory access for the NVLink domains, for this kind of NVLink domains for Grace Hopper, which is different than the previous generation NVLink domains, because right now the NVLink domain for Grace Hopper is crossing nodes. And for these NVLink domains, you have two ways to make the communication happen. One is peer-to-peer, and you have these parameters. And the other one is NICO. You have these parameters here. This is for NVL 256. Now, NVL 256 is quite a huge system. It's another extreme. The other extreme is NVL 1. Then the other extreme is NVL 256. Now, this system, this NVL 256, I haven't read any reports that has been that has indicated that this NVL 256 solution has been shipped to any customer. I have never got this kind of report from the media. Pretty much, I think this quite huge system, and I don't know what's the reason I haven't read this kind of reports from the media. Pretty much because it has never been shipped. That's what I think. But maybe I could be wrong. But anyway, it's too powerful. It's so huge a system. And then the industry moved to a smaller solution, which is NVL 32. So again, is the Grace Hopper reference architecture for NVL 32. NVL 32 means very simple. You have 32 nodes. Okay. And each node is a Grace Hopper superchip. And the code name for this superchip is CG1. For this node with only one superchip is called CG1. You have CG1 as one node. Okay. I reused the drawing to show the things, but I have modified here is that in underneath this 31, you can see another number with 256. So that's the same as the previous slide, but I modified this number to show what has been modified. Here is that for each NVL domain, you don't have 256 Grace Hopper, you have only 32. So this is called NVL 32 NVLink domain. Why we have this NVL 32 domain is very simple because all these 32 nodes plus the NVLink network, everything here could be fit into a rack. And this is the rack. This is the front view. We have 9 NVLink switches here. We have 8 dual GH200 compute trees. And we have another 8 compute trees down there. You have 16 compute trees, and each compute tree, you have 2 nodes, so you have 32 nodes, which 32 is the 32, 32 is the 32 for NVL 32, okay. And here you have a picture of the compute tree. Basically, inside each compute tree, you can have 2 nodes, the left-hand side and the right-hand side. In each side, you have 1 compute node. And this compute tree is going to be put here and also here. And then it's going to be put in the rack. So everything related with this NVL 32 domain could be put into one rack, plus the power shelves up here and down here. So everything related with this NVL 32 could be put into a rack. This is the beauty of this NVL 32 domain because it's modularized. It fits into a rack. That's easier from the production point of view. Okay. And then you have the logical wheel of this NVLink network. Basically, to interconnect all these 32 GPUs, what you need to have is you need to have 9 switches. You have 9 NVLink switches. You need to have 9 of them, and the 9 NVLink switches are going to be connected to the GPUs in the fed tree topology. So this is a fed tree topology here. And then basically for this interconnection network, you can run this equal communication library and you can do peer-to-peer memory access. Okay. This these 9 switches will be put here, but you are going to have quite a lot of links, cables. You have a quantity of cables. That's important. And where you are going to put these cables? Now, this is the rear view of this rack, and all these cables will be running here. So you have roughly the switches in the middle. You have the compute. You have the compute nodes. You have the compute nodes on the top. You have compute nodes. You have compute nodes at the bottom, and the cables will be running from the GPUs connected to the compute node to the switches. So you are going to have a big quantity of cables. Okay, the cabling will be at the rear side of the rack. Okay, so this is the NVL32. The reason to have the NVL32 is that it can be fitted into a rack. Okay, we have a look of this one. So this NVL32 enables all GPU threads in the NVLink connected domain. So you are going to have lots of threads. For example, we take one thread as an example. The thread can access to address up to 19.5 terabytes of memory, 19.5 terabytes of memory, which is the sum of all the memory, because you have 32 nodes, the sum of the host memory and the HBM memory, the GPU memory, the sum of them is 624 gigabytes. So 624 gigabytes multiplied by 32, you are going to have this is the total memory of all the nodes belonging to this NVL32 domain. And up to 900 gigabytes per second, because here this 900 gigabytes per second is here because each thread on any CPU can access all the memory, which is 19.5, and the bandwidth available is 900 gigabytes per second. And the memory access is going to be going through this NVLink network. This is a peer-to-peer memory access. And the bandwidth is 900 gigabytes per second. And then afterwards, so this NVLink domain enables the NVLink network of this NVLink domain for connecting 32 GPUs. This NVLink network, it has 450 gigabytes per second as the all reduced bandwidth. So 450 gigabytes per second as the all reduced bandwidth. Sorry, this is as, and up to 14.4 terabytes bisectional bandwidth. The bisectional bandwidth is 14.4 terabytes per second. Okay. If you still remember in the previous slide, we talked about NVL 256. We have noted the number for NVL 256. Now we have noted the number for NVL 32. Just remember that NVL 32 is 8 times smaller than NVL 256. That means the total quantity of the memory should be 8 times smaller than NVL 256. Okay, but the bisection, because the NVLink network is also 8 times smaller than the previous one, so the bisectional bandwidth will be 8 times smaller than the NVL 256. We need to check. Here is that we noted here we have 150 terabytes as the total memory and 115.2 terabytes per second as the bisectional bandwidth. We divide these two numbers by 8. We are going to have 19.5 terabyte as the total memory addressable by each thread, each GPU thread, and we have 14.4 terabytes per second as the total bisectional bandwidth of this NVLink network for 32 GPUs. But at the same time, we should notice that the bandwidth for each thread and the all reduced bandwidth should remain the same. This related with this NVLink is not related with the topology. We just need to check. We noted here is 900 gigabytes per second, and here is 450 gigabytes per second. It's the same as here. So that has not been modified. So everything is correct. This is for NVL 32. The communication is that within an NVL domain, you have two schemes to make the communication happen, NICO and peer-to-peer memory. Within an NVL domain or in between NVL domains, the communication should be done by using the MPI communication library. And the network, one choice of the network is the InfiniBand network. Yes, it's InfiniBand network. And for sure, the other technologies could be chosen. If you like, you can choose to use Ethernet as the network. But anyway, pretty much, you also need to run MPI on top of the Ethernet network. This is not a must-have. I mean, later on, we are going to come back to this point. Here, the communication between the domains and between the domains and in between each domain, the communication here could be something else. It hasn't to be MPI, it could be something else, but MPI is the most popular one, is the most promising one. Okay, this is NVL 32. Now we move to NVL 72. So why NVL 72? That's very simple, because we have a technology refresh. So now we move to Grace Blackwell. You know, for Grace Blackwell, for Grace Hopper, each Grace is connected to one Hopper GPU. But for Grace Blackwell, each Grace CPU is connected to two Black GPU. So it's connected to two Blackwell GPU. I modified the scheme I have shown in the previous slide to show the things. So you have 32 nodes per NVL domain. So it's called something is wrong here. It should be 35. It should be 35. I'm going to correct it later on, but we need to continue. Here, you have the domain is NVL 72. Now you have 72 GPUs connected by the NVLink network. And because each Grace Hopper superchip, you have two Blackwell GPUs, one Grace CPU. So 72 means you have 36 nodes. And we count here is 0, 1. Right now, I made a mistake. It should be 35 here. 35. 35 is the last one. 35 is the last one. So you have 36 Grace Blackwell superchip and 36. Each Grace Blackwell, you have two GPUs. That's going to give you 72 GPUs. Okay, 72 GPUs, and you use the NVLink network to interconnect all these 72 GPUs. You are going to have NVL72 domain, and this is interconnection network, NVLink interconnection network. Basically, you need to have 2 times more NVLink switches to connect all these 72 GPUs. And this is the network, is a fat tree, is a fat tree network. The fact is that all these 36 nodes could be fit into one rack, and this has been shown here by this picture. Is that this is a compute blade in compute tree. Inside each compute tree, you have 2 nodes, 1 and 2, and each node you have only one Grace Blackwell. So you have you are going to have 36 nodes. It means you need to have 18 compute trees. 18 compute trees. You have on the top you have 10 compute trees. At the bottom you have 8 compute trees. In the middle you have 9 switches, and each switch tree you are going to have 2 switches. So in total you are going to have 18 switches, and that's going to make the system. This is the front view of the system. Here you have got this rear view of the system. There it is, the rear view of the system. You are going to run the cables here. Okay, so we know that for this NVL72 physically is nearly the same as NVL32 with a few nodes more. This is I don't know why we have more nodes. We don't have a NVL64, but we have got this NVL72. Pretty much this is because the 72 is a good number for the NVLink network, and then the industry has decided. I mean, pretty much Nvidia has decided to go with NVL32, and it's good that this NVL32 could be fit into a rack, the same as NVL32 for Grace Hopper. For Grace Bell, you have a Grace Blackwell, you have this NVL72 as the reference design. And right now, this is the most popular products from the marketplace according to Nvidia for AI workloads. Okay. We have the number here is that the NVLink domain supports up to 72 Nvidia Blackwell GPUs with a communication speed of 1.2 terabytes per GPU. If you remember in the previous slide, we noted here you have 900 gigabytes per second, and it has been increased to 1.8 terabytes per second per GPU. I think this comes from the generation upgrade of the NVLink switch. So my NVLink switch, that's Grace Hopper 900 gigabytes per second, and right now for Grace Blackwell, you should have with communication of 1 point per GPU. So 800 gigabytes per second, 800 gigabytes per second. This performance increase comes from this NVLink switch, NVLink network generation upgrade. I think this Grace Blackwell, you have this NVLink switch has been upgraded to the next generation. I think right now it's generation 5, and the Grace Hopper should be generation 4, and this explains the performance increase. Okay. Anyway, this is for NVLink 72, and we need to have a look at this one. As I have said that right now, the NVLink domain is crossing multiple nodes. So right now, this NVLink domain is an MNNVL system. What does that mean? MNNVL means multi-node NVLink. So multi-node NVLink. So you can understand that this is multi-node NVLink domain. So NVL72 is a multi-node NVL domain system. Why? Because this NVL domain here is NVL72 is crossing 36 nodes. So this NVL72 is an MNNVL system. So basically, the understanding that NVL72 is a system with MNNVL domains. NVL72 is a system with multi-node NVLink domains. NVL72 is a system with NVL domains that's crossing multiple nodes. That's the understanding. Okay, and this one, here is the text from Nvidia. MNNVL system is a rack scale solution combining NVLink ARM-based Grace CPU, Nvidia Blackwell GPU, and NVLink NV switches connected through a passive backplane assembly. So the MNNVL rack contains 18 compute trays, 9 NVLink switch trays. Okay, and that's the performance parameters for these NVLink switches and the NVLink network, and for this one. So if you compare these 72 GPU, 4 GPU per tree, if you compare this ranking with the previous one, this is the same thing. Okay, so we need to stop here. For the super chip from Nvidia, starting from Grasshopper, starting from now, we start to have systems with NVLink domains with a big quantity of GPUs. And the most popular one is 72. And the maximum could be 256. We start to have these kind of systems. And one very important difference from the previous generation systems with NVLink domains is that right now, for this kind of system, for this kind of solution, the NVLink domain is always MNNVL, multi-node NVLink domain. Okay, so we need to stop here. I have listed all the possible solutions from Nvidia. And we can understand that right now, for these solutions, targeting this AI workload with these NVLink domains is getting to be the mainstream solutions for this marketplace. And this NVLink domain is going to pose to Nvidia and to the industry a little bit technical challenges to realize this NICO communication and the peer-to-peer memory access. These are the two topics we are going to continue. Okay, so we stop here for now. We have understood these MNNVL NVLink domains. Okay,